can be used. Okay, so now so in the last lecture we discussed about the construction. So as far as this chapter is concerned, semiconductor devices, micro devices. So construction of the device is important, then the working and application. These three things are there which are required to be understood by the students. Okay, so it's a purely theoretical. No numerical will come from this particular chapter and the last chapter. Okay, so pin diode, the symbol is similar to what we had. Okay, it's like this only. Now you are going to use this as what? Variable resistor. Okay, because you are going to use it as an attenuator. If you want to attenuate very high frequency signal, then how it can be used. Okay, so in the last lecture it was said that there is what intrinsic layer between P type and N type of semiconductor material, and just by forward biasing this P and N junction, you can control the amount of charge in the intrinsic region, and the conductivity of that particular layer can be controlled. So just by applying a particular amount of forward bias voltage, the amount of charge can be controlled. Means you're controlling the conductivity of intrinsic layer. So conductivity, if that can be controlled, it means that you are controlling the resistance. Okay, because they're related. Now circuit diagram. So here diode is there. So you are going to feed some signal from this side. So here there is input, and on the other side you will collect output. But of course the circuitry will not be very simple. Okay, because now you are applying two signals to this diode. One biasing diode, which will fix the amount of resistance offered by this diode, and the second, through the same diode which is already being applied by DC voltage, AC current will flow. Okay, so and these two signals must be isolated from each other, otherwise they're going to disturb each other. So we are knowing which components are required for that. So capacitor, that is one thing. Okay, on the input side and on the output side. So here for the AC signal, the capacitor will act as a short circuit. So you can see that when you're applying a signal, input signal from through the capacitor, it will appear, it will reach the diode, and finally the output capacitor will short circuit and you will collect the output. But now how to deal with the DC? So for that, one inductor here, okay, like this, and this is taken as a reference point, and one inductor here. I will write here only. Okay, like that. So this is DC. So the role of inductor is what? It offers zero reactance or zero resistance to the applied DC signal. So you can see that DC, the positive is applied here, and the negative, or you can say the lower potential, is your ground point. So the diode will be what? Forward bias. Now how much resistance you want, accordingly the DC voltage can be adjusted. Now whatever AC signal is coming from the input, the capacitor is going to act as a short circuit, but this inductor will behave like open circuit. So no AC signal will reach to the DC. So DC voltage will not get disturbed. Okay. Similarly, on the output side, when the AC signal passes through the diode, it will it won't go through the inductor and will get grounded. It's not going to happen because the inductor is going to offer high reactance for the RF signal. But the capacitor will act as a short circuit. So without any attenuation, that signal will be appearing on the output side. So the entire attenuation is offered because of the diode. Okay. And the capacitor, it blocks DC. So whatever DC voltage is available, that will never reach to the output side, and it will never reach to the input side. That is the high frequency source. So the two signals, they are isolated from each other. They are going to mix only in diode. Okay. At no other place they are going to interfere with each other. So this is called as the series arrangement of the pin diode. Okay. Now, there can be shunt arrangement, but the concept will remain same. You need to have a diode and one capacitor, multiple capacitor and multiple inductors, just to isolate the two signals. Okay, though both the signals will be available in only diode, and in other part of the circuitry, these two should be isolated from each other. Now we'll move to the Schottky diode. So for Schottky diode, we'll use one diagram. Okay, this diagram. See, the issue with the ordinary diode is that in the reverse cycle, means in the positive half cycle, the ordinary diode is going to act as a short circuit, and whatever AC signal is applied, that will appear on the output side. But in the reverse bias case, what happens that whatever minority charges are there trapped in the earlier cycle, they will start flowing in the outer circuitry and will set some current. So you can see that in the reverse bias condition also, there is what conduction of the current, but of course they are going to exist for a very small amount of time. So if suppose the time period of the signal and the time in which this minority carriers are getting sweep out of this PNN region, if that becomes comparable, so you can say that in the negative half cycle also the diode conducts, which we don't want. Why? Because the rectification ability of the diode, it ceases as the frequency increases. And I think the idea was given that around somewhere around 3 kilohertz or 5 kilohertz, the diode, it can show you the complete flow of what AC signal. Means rectification will not be there. Like we have been, you have learned that in the first year that in the positive half, this if you are applying a AC signal, you get rectified output. Okay, so either positive half will appear or the negative half will appear depending on the polarity of the diode. But at higher frequency, because of the minority carriers which are trapped in N and P region, the sweeping of those charges will take place in the negative half cycle. It is just like the discharging of the capacitor. Okay, so you know that if you are in the positive half cycle, if the capacitor is charged, okay, so in the negative half cycle, the capacitor start discharging. So same thing is going to happen here, and this discharge current or discharge charges from the diode, it flows in the external circuitry, and you can say that the diode is not going to behave like a rectifier. Okay, so if suppose you want to rectify high frequency signal, then what can be the solution? The simple solution is what? You should not have any minority carriers. Now, what are these minority carriers? So suppose you are having P-type extrinsic semiconductor material. So majority carriers are what? Holes. And in case of N-type of intrinsic semiconductor material, the majority carriers is forward bias. Then from P region, all the holes, they move towards the N region. And the moment they enter into the N region, they are treated as minority carriers. And similarly, when the electrons from N region crosses the depletion region and enters into the P region, all these electrons are treated as minority carriers. Okay. So in P region, there is electron which is acting as a minority carrier, and in N region, the holes are there which are acting as minority carriers. When the negative cycle comes, or if the reverse bias, if the diode is reverse bias, then what happens that further flow of electrons from the N region and further flow of holes from the P region, that stops. But from the earlier case, whatever holes were trapped in N region and the electrons were trapped in the P region, now since they are minority carriers and this potential barrier, it supports the flow of minority carriers across the junction. So what will happen? These trapped electron and holes in N region and P region respectively, they can flow without any hurdle, and there will be what? A flow of current in the entire circuitry. So that minority carrier should not be there. So in order to avoid these minority carriers, the modification in making of this diode that is done. So now, as you can see in this diagram here, now we are going to have, instead of having P, N, and two different materials, we are going to have N and N material. But of course, one is semiconductor and one is metal. So here I have written M on the right hand side. Here it is what uh, energy band diagram for metal, and these two are not connected. Okay. So in the metal, which I have represented with the help of M, so you can see that shaded region, it is nothing but the overlapping of valence band and the conduction band. Okay, so it means that the electrons, they are having sufficient energy and they are free to move. Okay, and the Fermi energy level is what between it is buried in the conduction band, which means that there are huge amount of electrons and they are free to move and can contribute in the conductivity. And so I was in whiteboard mode only. Okay, so here now you can see that the left side I have written M, and on the right hand side on the top I have written semiconductor. So this is nothing but the energy band diagram for the metal and semiconductor separately. Now we are going to make a new diode, which will be not comprising of P and N type of layer, but metal and N type of semiconductor material. Okay. So on the left hand side, I have shown a shaded region, box is shown, which shows the overlapping of conduction band and the valence band, both. Okay. Because the energy of the electron in case of metal is so high that both the bands, they are overlapped, and that is how we represent a conductor. And the Fermi level is what buried in the conduction layer, which shows the near the Fermi level, it shows whether the material is conductor or is there any possibility that it can behave like a conductor or not. On the right hand side, so if the Fermi level is buried in the conduction band, it means that it is a metal actually. So on the right hand side, you can see that the Fermi level is just below the conduction band. It means that there is good possibility of conductivity, but some external this trigger is required. Okay. Now the major thing here is what actually I have drawn a dotted horizontal line on which I have written free electron energy level. Okay. So if you look at the metal, then from the top, this box line, whatever box shaded box is drawn, the top line, and the dotted line which is drawn and written free electron energy level. So there is a huge gap between these two, which shows that if you want to knock out one electron from the metal and you want to make it free so that it can move in free space, then there is a huge difference between the top line of that shaded box and that dotted line. It means that a larger amount of energy is required for electron to liberate from the metal. But if you look at the semiconductor side, then the top line is what the conduction band line, WC line, and above that dotted line is shown that free electron energy level. So if you want to knock out one electron from the semiconductor and you want to make it free to move in the free space, then the energy required is what lesser. It means that if you're having N type of semiconductor material, then the electrons, they're having more energy than the energy contained by any electron which are present in the metal. Okay. Now when these two materials, they are clubbed together. So now one is metal and another is what semiconductor material. So you can, as I said, that the energy level of the electron of the metal. So what happens now? The N type of semiconductor material, and they will start moving towards into metal. So there will be continuous flow of the electron from semiconductor to the metal, not from metal to the semiconductor. Okay, just because this difference in the energy level. Okay, electrons in semiconductor material, they are having more energy than the electrons having energy in the semiconductor in the metal. So there will be continuous flow of the electron from the semiconductor to the metal, not from metal to the semiconductor. And if the electrons from the semiconductor, they are moving into the metal, so what will happen that since the N type of semiconductor material is losing electron, so it will turn into what? Positive ions. Okay, the electrons which are entering into the metal, So the electrons which are at the border of the N type of semiconductor material, they will first enter into the metal. So that region is losing electron. So if the electron is lost by N type of semiconductor material, so there is what deficiency of electron. So it means that now the positive ions are appearing at the junction. And since the metal, it has gained the electron, so the metal, it will become what? Negatively charged. Uh, it will gain negative charge, excess negative charge. So now a junction will get created, N type and P type. And there will be continuous flow of electron as long as the junction potential created at the junction is not sufficiently high to stop the further flow of the electrons from semiconductor to metal. Once the sufficient number of electrons are crossed, or you can say that the barrier potential increases to a level where the electrons now they will uh, uh, face a sufficient amount of oppose, and because of which the further flow of the electron from the semiconductor material into the metal will be stopped. Okay, just like your ordinary p-n junction diode. Now you can see that on the left hand side, which is metal, there is electron, and on the right hand side, still once again you are having semiconductor material, but electrons are once again the carriers. So you are having only majority carriers. There is nothing like minority carriers. Okay. So if this diode is forward bias, how to forward bias this diode? N type of semiconductor material should be connected with the negative polarity of the biasing source, and the metal should be connected with the positive terminal of the source. So this condition is called as forward bias. So if the potential is sufficiently high to overcome the barrier potential, then there will be flow of electrons from semiconductor material to the metal, and there will be flow of electron. But if the reverse is done, then the barrier potential is going to increase, and the further flow of the electron will be stopped. And but the moment you apply a reverse bias potential, there is nothing like minority carriers which are trapped. So discharging kind of thing is not going to take place, which was taking place in case of p-n junction diode. So if discharging kind of thing is not there, it means that when the diode is reverse biased, there is no flow of any carrier, and therefore there is no current in the negative or in the reverse bias condition. So it means that this particular diode is not going to conduct at all in the reverse bias condition, and this is how we avoid the conduction of current in the negative half cycle. So these diodes are called as what? This high frequency diodes, because they can be used as a rectifier at high frequency also. So this is all about the Schottky diode. Okay, application of this diode. See, working is similar to your ordinary p-n junction diode, but when the reverse bias potential is applied, then there is nothing like minority carriers. So in the reverse cycle or in the reverse bias potential, there is no flow of any carrier. That is the only difference. Otherwise, this also is used as a rectifier. The earlier was also used as a rectifier, but this is suitable for high frequency application. Next is simple concept is there, but of course the circuit is very tedious for this, because sometimes when we go through a theory, we find that it is very simple. So that may be simple to understand, but difficult to implement, and that generally happens in case of RF area. Okay, so now we'll see what is the parametric amplifier. So parametric amplifier is simply, it's not your transistor amplifier, but it's a amplifier using a capacitor. Okay, and why the name is parametric? Because we are going to use one of the parameters of the capacitor to gain amplification. Okay, so here I have written, you can see on the top right side, I have written formula for the C. C equals to epsilon A by D. Okay, so here uh, D, already we have gone through what? Variable capacitor, okay, varactor. So the varactor concept is used here. So varactor and varactor, it was discussed that by applying certain reverse bias, reverse potential across a diode, the depletion width can be controlled. That depletion width is nothing but your D. Okay, so if you can vary D, then the capacitance can be changed, and if the capacitance changes, then the reactance can be changed. Okay, so there it was variable capacitor, but here this concept we are going to use for the amplification of the signal. Now, so one thing you have to keep in mind that you are going to vary D electronically, not mechanically. And there is one more this relation which relates charge and potential of a capacitor. So it is V equals to what? Q by C. Okay. Now, if the C changes, suppose you have applied some potential on the capacitor. So of course, some charge will get induced on the plates of the capacitor. Okay, that will be Q. So without disturbing this potential, if you're not disturbing the potential, then the charge will not get disturbed. But if suppose you are varying C, suppose the C increases, then what will happen? That the potential will decrease, right? And if suppose if the C reduces, then the potential is going to increase. But now from where this change in the potential is occurring? See, if you want to vary the potential, that the charge should not get disturbed, but the capacitance should get changed. Okay, because if suppose capacitance is changing and Q is also changing, then that ratio will remain same and the potential is not going to change. So you have to keep your charge fixed. And if you can make any change in the capacitor, then only the voltage can be influenced. So simple technique is what? Just vary the capacitance. So amount of charge will remain same and the potential can be changed. Now the unit of potential is what? Joule per coulomb, right? So that per coulomb, that charge is what? Constant. But if you can increase the amount of energy, then the potential will increase. But from where this energy will come? So by changing the distance D or by changing capacitance, if you're making any change in the capacitance, so that can be done only by changing the D. So that change in the D will come from what? From varying DC potential. So that potential, once again, the potential is what? That is the amount of energy spent per unit charge, right? So when you're changing the capacitance, so that for the sake of change in the capacitance, you are applying certain amount of, you are spending some energy, and that expenditure is done by the DC source. So actually you can say that the DC energy is getting converted into what? That change in the potential, or you can say change in the AC, just like your transistor amplifier. There you are applying a weak signal, and that weak signal, it absorbs or it takes energy from the DC source, and you can say that the finally whatever signal is collected, its energy level is very high. So same thing is going to happen here, but not using transistor, but using a variable capacitor. Okay, so let us see the mechanism first, and after that we will go to the circuitry. So here one input signal is there, as you can see. Okay. Now input signal that we want to amplify. So how it is achieved? By changing the capacitance. Now how to change the capacitance? So there is one square pulse that is called as what? Pump signal, that is responsible for all this. So you can see that during the positive half cycle. So what happens that during positive half cycle, this first C is fixed. When it is forward bias, D is very small. Okay, because if a diode is there and if it is forward bias, we are using diode as what? Variable capacitor. So if I'm applying positive potential, then the diode is forward bias. So depletion region width, it will become very, very small, right? So you will have some larger amount of capacitance. That is the initial value, suppose, of the capacitor. And now that capacitor is exposed, or it is applied with this input signal. So that capacitor, it starts charging. Now that charge is what? Charging of the capacitor is shown in the third graph. I have written that amplified voltage. Why I'm calling this as amplified voltage, that very soon will be revealed. But during the positive half cycle, when the pump signal was positive, that capacitor, it charges and it follows the shape of your, or not exactly, but almost the shape of the applied input signal. Okay, and the moment the signal achieves its peak value, So let us look at this pump signal, what happens. That immediately the signal changes its polarity, pump signal. So it becomes what? Negative. So the moment it becomes negative, what is going to happen? Look at the equation, first equation. The D is going to increase because now the diode is what? Reverse bias. So D increases, so capacitance is going to drop. Now look at the second equation. Since the capacitance, it has become smaller. Now the charge, which is being induced because of the applied input signal, that charge is fixed actually, but C has got reduced. So what will happen there? There will be what? Suddenly there will be change in the voltage, right? So that voltage change I have shown here, that sudden change is there in the voltage. And now, since the input signal, it is there only, now the capacitor, it will follow the input signal, but with a larger voltage, okay? And the moment the signal becomes zero, then the polarity of the pump signal changes. And once again, the actual value of the initial value of the capacitor is restored. That is what? Forward bias. So you can see that the this diode is forward biased only when the applied input signal, it is zero. Okay, and it is a reverse bias when the positive peak or the negative peak occurs. So you can see that there is what? Change in the magnitude of the input signal when it is passed through a capacitor. Now you must be thinking that the applied input signal is a sinusoidal signal, but the amplified, it is what? There is what? Lot of distortion. That is okay. Distortion is there, but amplification is done. Now, in order to avoid this distortion, what you can do, you can pass this signal through one tank circuitry, which is tuned to the applied input frequency. So now in tank circuitry, we are having what? Inductor, right? The characteristic of inductor is what? It does not allow sudden change in the shape of the signal. So reshaping of the signal is going to take place now. Okay. So whatever distortion is there, that can be eliminated, and your signal, it can be made very smooth, and it will be just like your applied input signal. So this is how we achieve this amplification using parametric amplifier, and that's why the name is what? Parametric. Here we are using D parameter for amplification process. Okay. Now we'll see the circuitry, because this is on the basis of what? Only the diagram. Input signal is there, pump signal is there, then the amplifier output is there. But what about the circuitry? How the circuitry is going to look like? Okay, so now let us have a look at the circuitry. So your capacitor, okay, you are using a capacitor, right? So this is that capacitor. Variable, this is the equivalent circuit diagram. This is a variable C, and this is the resistance from the same diode. Okay, now as I said that this capacitor is exposed to two different signals. One is what? The signal which we want to amplify. Okay, so amplifying, there is a this is almost like a filter only, okay, because you're going to work at certain frequency. Okay, so that is selected with the help of this LC filter. Okay, and the input signal is there, right? This, and there is another role of this LNC. Huh? Now, what can be the other role of this LC? We have already discussed that. We are just to recall it, or I will disclose at the end. So one capacitor here, once inductor, then resistor. Resistor, you can say this is the source resistance. Okay, and one more signal is here. So this is why your pump, and here this is signal. Okay, and on the output side, I said that you should have one filter tuned to what? Your desired signal frequency. Okay, and this is the load. So I will call this as RL, and you get what output across this. Okay, so output is there, then pump signal is there, that signal is there. Now what is the role of LC? So see, you are using what? Biasing potential to vary the capacitance of the diode. So that potential is what? DC in nature. Okay, square pulse is there, right? So that should not interfere with what? The other signal. So L and C plays important role in that, right? So this is your circuitry for the parametric amplifier. The pump signal is there, and what? Your signal frequency is there, which is applied to a variable capacitor. Now, the nature of the variable capacitor is what? Non-linear in nature. If you remember the last lecture, so it was something like this. This is what voltage versus capacitance. Okay. So if there is no potential, there will be what? Some inherent capacitance because of the this depletion region, PN junction. Okay. So that capacitance is there. If you apply more and more reverse bias, then the D increases and the capacitance it reduces, right? So you can see that this behavior of the capacitor is what? Non-linear in nature. So what happens that when you apply signal and the pump signal across this parametric amplifier, because of being in non-linear in nature, this diode is going to generate three different signals. One will be what? That signal whose frequency is exactly equals to the applied signal which we want. And there will be another signal which will be some frequency and the difference frequency of the applied two signals. Okay. So there will be what? Three different signals will be there. Three different signals will be there, right? So if you want to filter out all this, so that's why you need to have what? One filter also. That's why L and C is there. Okay. Otherwise, you will have all the three components. Now, which component is you want? Accordingly, you can design a filter. You want to have the same signal frequency or the sum you want, or you want a difference. Okay. So any of the frequency can be taken out from this. So this is about what? Parametric amplifier. So what is expected? The concept, the circuit diagram. These two things are expected if it is asked as a theory. Okay. Now we can move to the another topic, that is Gunn diode. So whatever part is possible today, I will finish it. Otherwise, we'll continue the same topic in the next lecture also. And by next week, this chapter will get over. Okay, semiconductor transistors are left. So BJT we have already discussed. FET is left. So two FET transistors are there, and this three more diodes are there. Okay, so next week, because I will be using PPT. Okay, so I prepared notes for that. I will be using PPT, so we can finish it in the next week. Now the last topic I said that diode that we are going to see, but Gunn diode. And at the end, in the earlier lecture, I said that whatever diodes are there, which are used as what? Amplifier. Okay, so the concept was not discussed. So once this Gunn diode topic is finished, we will see the application of the negative resistance diode as an amplifier. Okay, so at the end, because all are going to have the common circuitry, so I will discuss that part at the end. So let us see how this Gunn diode works actually. Even though the name is what? Diode, so we expect what? That it will have one positive terminal and another is a negative terminal. So generally when we call as positive and negative terminal, so we feel that, okay, there will be one P type of layer and the another will be what? N type of layer. So the terminal connected to the P layer is anode, and the terminal connected to N type of layer is nothing but cathode. But in Gunn diode, there is nothing like this, because the material, extrinsic material which is used to make this diode is only N type. Okay, only N type. P type, we don't use P type of material here. The simple reason is what? The mobility of the holes, that is what? Very less. And the mobility of the electron is very high. So that's why we are going to use N type of extrinsic semiconductor material only. Okay. Uh, Now the name is what? Gunn diode. Okay. So it's it is not GUN, but it is GUNN. Okay. So Gunn diode. It is the name of the inventor, Gunn. Okay. So he is the person who invented this diode, and the material somewhere around 60. Okay. This diode was discovered by this person. Okay. Now the material, as I said, used is what? N type gallium arsenide. Okay. The reason is what? The mobility of electron in the gallium arsenide is very high, somewhere around 4500. Okay. Yeah. Yes. You have any doubt? No. Okay. Now, when the Gunn was experimenting with the N type of gallium arsenide sample, then certain distinct behavior he noticed of this material, and that led to the development of Gunn oscillator. Okay, so first, what he observed that this is what the x-axis is going to represent electric field. This electric field was applied across a sample of N type of gallium arsenide. Okay. The specimen which was used by that person was 2.5 into 10 to minus 3 centimeter in length. Okay. And the vertical axis, it represents the velocity of the charges which are there in the gallium arsenide. So you observe that initially up to certain voltage, okay, somewhere around 3 kilovolt per centimeter, less than that. If the electric potential increases, then the velocity of the electron, that also increases. Okay. So if this kind of behavior is there, it means that the velocity is what? It is proportional to the applied electric field intensity. So if you remember, the velocity, it is what? Mobility into the applied electric field. So if mobility of the what we expect that the mobility of the electron in a material is fixed. Okay. So mu is constant. So if you apply electric potential, then the velocity should increase. So any material which is having this kind of behavior, they are what? They are going to show you what? Ohmic behavior. That is what? Positive resistance. Okay. But after that, what happens that? So even if the potential increases, then there is what? There is hardly any increase in the potential, velocity. But it was observed that a drop in the velocity was observed. And after that, the velocity, it becomes what? Almost constant. But a drop in the potential, in the velocity, that was observed. So if we are increasing electric field intensity, so by this formula, the velocity should increase because you are increasing the electric potential. But somewhere at what? 3 kilovolt per centimeter. Okay. So if the potential is this much, the electric field, if it is this much, then the velocity, it starts reducing. So this was the first observation which he made. Now the second observation, what he did that after knowing that this is what is happening inside the N type of semiconductor material, gallium arsenide. So he started experimenting that sample at this 3 kilovolt per centimeter and beyond that. So he observed that if a pulse is applied, now this time it is time versus magnitude, time versus I will call it V. In the book, it is mentioned that the current behavior is observed. Okay, so a pulse was applied of certain duration, right? And this is the pulse which is applied to n type of gallium arsenide sample. And then he found that on the output side, the same pulse should appear, but he observed that that pulse it contains fluctuation like this. It's not a straight the pulse. And if it is magnified, suppose, so if I magnify this part, then there is something like this. So oscillation was observed. Okay. Now the period of oscillation that was measured. Okay. So if I say that this is the period, okay, so one period is taken. So this period, it was equals to what? Time taken by the electron to pass that sample. Okay. So if suppose the size of the sample of that gallium arsenide is suppose this L, and the velocity was taken from this graph. Okay. So it is what? Length divided by velocity. Okay. Length divided by velocity. This is going to give you what? Time. So inverse of time is nothing but the frequency of the signal. So that period of the oscillation and this time both were same. Then he predicted that if the length can change, then the period of oscillation can be changed. And the significant observation was that if you apply a pulse which can create a electric field intensity of 3 kilovolt per centimeter, then there is possibility that this material can produce oscillation in the microwave range. And this made the base for what? The invention of diode, so Gunn diode, and which is used as what? Oscillator. Okay. So now we'll see how to use this as an oscillator. Okay. Only 4-5 minutes are left. Why the velocity changes? So there is what? Different models are proposed. So we'll go through one of the models. Once this part is clear to you why the velocity drops, okay, then we'll go for how this particular behavior of the Gunn diode can be used in making oscillator. So that will be the end of this topic. Okay. So if any queries there, you can ask.